Dear colleagues, I am Tom Wenisch of the University of Michigan and Google. I am honored and humbled to be named to receive the 2021 ACM SIGARCH Maurice Wilkes Award. On behalf of myself and the many students and collaborators that contributed to this work, I'd like to thank the computer architecture community for this recognition. The selection committee cites this award for contributions to memory persistency and energy efficient systems. The body of work underlying these words is a tale of many collaborations with students and industry partners, and over the next few minutes, I'll give a very abbreviated history of those collaborations. I'll speak first to my collaborations on energy efficient computing. My interest in energy efficient systems, and more broadly in data centers and warehouse scale computing, dates back to 1998, well before I entered graduate school, to an undergraduate internship at American Power Conversion in West Kingston, Rhode Island, where I collaborated with Jim Van Gilder, a mechanical engineer studying data center thermal topology estimation. My time in grad school from 2001 to 2007 spanned the dot-com boom and bust and the start of the transformation from grossly inefficient data centers to the hyperscale infrastructure of today's cloud computing. When I was on the job market in 2007, the wonderful conversations I had with colleagues in industry and academia convinced me to focus my early career on energy efficient enterprise systems. In particular, Partha Ranganathan, at the time at HP Labs, discussed the challenging problems he was working on to design efficient, disaggregated blade servers, and encouraged me to focus on making enterprise computing green. At Michigan, I convinced my first PhD student, David Meisner, to pursue this new area with me. One of the things my advisor, Babak Falsafi, taught me is the importance of coming up with good names for research ideas. Our very first paper at Michigan had what is probably the best name of my career, PowerNap. PowerNap observed that in servers, threads alternate between 100% busy and idle at extremely fine timescales, but that most server components still burn a large fraction of their peak power when idle. This work kindled interest in a variety of follow-ups to develop techniques to make server components sleep more effectively when idle. PowerNap also caught the attention of Luis Barroso at Google, who invited David to an internship to examine server power management techniques at Google scale. At Google, David developed a taxonomy of low power techniques and studied their impact on web search. This collaboration shifted the focus of our work from idle low power modes to active low power modes, as increasing core counts and multi-threading made it harder and harder to find opportunities to put a large fraction of a system to sleep. Our work on active low power modes grew into a multi-year and multi-student collaboration with Riccardo Bianchini, then at Rutgers and now at Microsoft, examining active low power modes for main memory, the next largest energy hog after the CPU. The final collaboration on energy efficient computing I'll highlight is with Milo Martin, then at the University of Pennsylvania and now at Google, on computational sprinting. In this effort, we studied chip designs that transiently exceeded their thermal limits to try to race to idle and buffer the excess heat temporarily in phase change materials. In the video clip you see here, you can see wax melting as we run the processor underneath well above its steady state thermal limit. The selection committee also cited our group's work on memory persistency. I'll comment briefly. In 2012 and 2013, my PhD student, Stephen Pelley, had been studying the applicability of emerging persistent memory devices to database systems several years before we had the 3D crosspoint devices that are available today. I had long had an interest in memory consistency models and sophisticated implementations of both strict and relaxed consistency. This confluence of ideas led us to realize that the ordering constraints needed for correct synchronization of shared memory programs governed by memory consistency were different from the ordering constraints that writes to persistent memory needed to follow to enable correct recovery after failure. That realization suggested we could build systems that decouple the memory consistency model from the ordering model for writes to persistent memory. We called this new ordering model memory persistency. The initial concept then was extended over 2 more PhDs. These works looked at different hardware implementations of memory persistency and how it can be applied both at the ISA and programming language levels of abstraction. I'd like to close by thanking all the PhD students I have worked with, including those whose works I did not have time to highlight today. I'd also like to thank all my colleagues at both the University of Michigan and Google Madison who have made all of this work possible. I'd like to thank my advisor, Babak Falsafi, and the many mentors who have guided me throughout my career. And thanks also to the myriad co-authors of my research, 163 of you, according to DBLP. Finally, I'd like to acknowledge all the industry sponsors and funding agencies that supported this work and enabled the many collaborations underlying this story. With that, I thank you all for your attention. And don't forget to like the video and subscribe to this channel.